Uh, my name is Steve Skeena. This is CSE 373, the Introduction to Algorithms, and I'd like to welcome you all to here on this very unusual year of teaching online. Let me get started with, I want to start off by talking about the course mechanics, but I want to encourage questions from people. I've never taught online before. In fact, that's probably my biggest thing to learn today. I've never taught online before. I know it's going to be different than usual. I will need your patience. I will also need your interaction. When I teach 373, I like the fact that there's questions going on in class. I like the fact that, so I encourage people to open up their mic if they want to have questions. If this gets to be a problem, I will let everybody know and I'll change the policy. But from now on, what I'd really like to see, if people could, if they ask questions, if they speak up. If you don't want to speak up, you can try asking on the chat. It's hard, I find it a little hard for me to follow the chat at the same time that I'm following the lecture, but let's see how we do. Okay, any questions so far? Okay, good. So let's try this thing again. So let me start off with the syllabus and the mechanics. The first thing to note is that all my material is on my website. So my syllabus, which you all should get, is on the website, which I believe is, let me see if I can write this. And unfortunately, I may be having some trouble with the writing of this now. My tablet's in a little bit of a funny state. So let me try one more time. And if I fail with that, then we'll just move on. Anyway, the website is, if you go to Skeena's website, it would be www.cs.stonybrook.edu/tilde Skeena, that's SKIENA, /373. Okay, I see it's over on the, on the chat thing. And over there, you will find my syllabus, which I strongly encourage everyone to read. This is the syllabus. Actually, are people seeing me in the corner of the eye? Or is it just the screen? Yes, okay, good. Okay, so I'm seeing that's good. So let me just read the syllabus to you guys, just to make sure we understand what the deal is. This is 373. The prerequisites of the course are data structures, which is 214. And linear algebra. I'm hoping everybody has that and is registered. If there are very special cases, you can come by and talk to me about it. But I strongly believe people should have the prerequisites before taking courses. The textbook is this thing. Okay, this is something called the Algorithm Design Manual, which I think is a really good book, partially because I wrote it. And it is an introduction to algorithms that is designed to be accessible. Algorithms is a technical field. It's a hard area. There's a lot of thinking involved. I try to minimize the amount of math that we need. Okay, but of course, this is still a mathematically oriented subject. But I think algorithms is it's the most exciting part of computer science. And I hope people will enjoy that. That is the, the textbook. And I strongly recommend people get the textbook and read it. I like textbooks. I wrote it so it could be read, things like that. The grading for the course, we are going to have 5% of the grade is going to be daily problems. Every day at the beginning of class, I am going to go through a problem that is assigned on I have published a list of all the daily problems, okay, on my, on my website. My hope is we will stay in sync this semester and that we will be covering, the given problem on the given day. But there will be one problem at the beginning of class every day. before class, you are supposed to upload your solution, okay, to it. These solutions are not graded. These solutions are counted. So if you want, you can submit an answer that has nothing but a blank sheet of paper, okay? And that will be fine. We count how many times there have been submissions. That said, I find that it is very, very useful for students to count, to try to think about the problem before I solve it in class. Because again, part of algorithms is a tricky subject. Trying to see where you go wrong is an important part of learning these things, what kind of traps you fall into it. So the daily homework problems will not be graded. The daily homeworks will be counted. And they've got to be uploaded to Blackboard. I believe it is all set up so that it's ready to take your first daily problem on Thursday. I try to make the submission period for the daily problems to start slightly before class, okay, running till the start of class to encourage people to look at the problems before class. We will count the number of daily problems. The total amount of credit for that will be 5%. Any questions about the daily problems? Okay, that counts for very little of your grade. But I've done correlation analyses where the semester averages correlate very strongly with the number of daily problems people turn in. If you think about these things and try to keep up, you will be doing much better. 15% of the grade is going to be on homework assignments. There's going to be a total of 5 homework problems, okay? Some question about, can we start the daily problems early? You could start the daily problems as soon as you want, okay? You have my whole semester's worth of daily problems, but you can only turn them in before class. And I encourage people to, again, to keep up with these things as opposed to trying to say, oh boy, I'll get the semester daily problems done early. It's supposed to stress what you worked on the previous lecture. That's kind of how they're scheduled. 15% is the homework assignments. That's 5 times 3. Each homework assignment is worth 3% of your grade. 4 of the homework assignments will be, paper exercises that you're going to submit over Blackboard. Okay. You're allowed to do these 4 with your partner. So I'm allowing people to work in pairs. You and your partner can submit the exact same set of solutions and should submit the exact same solutions. Okay. You'll see what happens when it's time to turn in the first homework. I want people to work in pairs. I think algorithm problems require thinking. They require kibitzing back and forth between people. And I think that it's easiest to understand where the traps are and see what's going on if you work with somebody. So my strong suggestion is that you find a partner that you want to work with on your homework. Not 2 partners, 1 partner. And if it doesn't work out, if your partner turns out to be a louse and doesn't do any work, you're allowed to break up with your partner. I'm not willing to be a marriage counselor, okay? I don't want to know about these things. If you have problems with your partner, break up and find another partner, okay? But any questions about the homeworks? Okay, and again, the homework problems, the exams are going to be made up of things like the daily and homework problems, not the same ones. Okay, maybe I might give one that was a homework problem or a daily problem. I don't put it past me. But similar kinds of things are what's going to be on the exam. So that's kind of important. The bulk of the credit for this semester is going to be on the midterms and the exams. There are 2 midterms, each count 25%. There is a final exam, it counts 30%. Okay? And like I say, the exams traditionally are, mostly homework-like problems. I also have a multiple choice section, okay? But the interesting thing is the homework-like problems. Any questions about the exams or the grading or anything like that? How I come up with a number? Okay, one thing that as I go through, again, I'm encouraging everybody to read the syllabus. One thing that I want everybody to understand when it comes, will the exams be handwritten? The answer is we will figure out the exact submission technology when, what you call it, the exact submission technology we will figure out over time. My plan is that the exams will be, again, they will be online, they will be scheduled, they will be synchronous, they will be, you know, and they will be presumably part multiple choice and part written thing. It might be that we decide to make the written be something you type in instead of write by hand as usual, okay? But we will figure out the details as the time comes up. Any questions? I'd like to hear by voice if somebody's got a voice in this class. Any voices? Okay, I hope people discover that because I think that's the better way to interact in a class like this. Okay, what else can I say? One thing about my midterms is that the averages on my midterms are designed to be hard, okay? That doesn't, you know, that the average on my midterms is almost always in the 60s, almost always in the mid 60s. I calibrate it pretty well. Now, some people see this and say, oh my God, you know, God, they get terrified when they get a low grade. Recognize that I curved the semester grades and that my median grade in the class is going to be a B minus. So what grade are you getting? What if you got, let's say, a 65 on the midterm, what is the most likely grade that you're going to be getting in the semester? What should it correspond to? Does anybody have a voice?
A B minus.
A B minus, that's right. Now, is it that people often get these grades and they panic? They say, oh my God, I got in the 60s, am I failing? If you get in the 60s on the midterms, are you failing?
No.
No.
No. What are you getting?
B
B
minus.
minus.
I didn't hear that. Can someone say that louder?
B minus.
Okay, so this is something that I need people to understand. The exams are hard. There will be students in here that will get in the 90s on them. And that's one of the reasons I make them hard, to make sure they get a challenge. There will unfortunately also be people who will get in the 20s on it. Those are the people that are in trouble. Okay, any questions about that? Again, I try to make it so I know that people need a C or better to pass this class to get it for your major. I do not like to award below that. Okay, if there are people who will, what you call it? You know, if people do the homeworks, if people show that they're, you know, on the exam that they have something going on, that they're doing something. Okay, I'm usually going to try to find a way to give them a C or better. Okay, any questions? Okay, and yes.
Someone was asking in the chat whether or not the exam will be handwritten.
The exam will be, I don't know. So this is an online, in a normal world, my exams would be handwritten on a sheet of paper. And there would be a Scantron form for the multiple guest part. Now, you guys are going to be taking this remotely. I haven't figured out if I am going to somehow have people write by hand and upload images, or more likely have them enter in text boxes. Okay, this is something that we will figure out. Okay, you will know before the midterm. Any other questions about these things? Okay. I'm not going to keep going through the rules of the game in the.
Sir?
Yes.
One student was asking if we'd be using a lockdown browser.
We will work out the exact details, but yes, my hope would be that we are going to try to run this as much like a prison as we can, and that there will be some form of online lockdown browser, exam synchronized, okay? But we will figure out the details as time goes by. This is the first time I've taught like this. It's, going to, it's going to take some patience, but that is my vision.
Okay.
Okay. And if there are some wild reasons why I should avoid doing it that way, you can send me email about that. But that's at least my current thinking.
Thank you.
Okay, good. Okay, rules of the game. Again, I recommend, I like my book. I recommend people would get my book and read my book. Okay, the book is designed to be read. And I think that's an important thing. The lectures I'm teaching on Zoom, you should be able to get the recordings on Blackboard, and I am hoping to make them available on YouTube fairly much in sync with this. But you're better off watching it. There's some other accoutrements if you watch it in Blackboard online. So I think that's probably the best place to do it. Any questions about that? I revised the slides somewhat this year, but I mean, I think basically conceptually, this is very similar to what I do every year. If you want to watch some of my old lecture videos of these things to see what I looked like when I was a little younger, those are also online. But I encourage people to do a live performance so we can have a questions. Any questions? Okay, what other things can I tell you? I told you about the course website at www.cs.stonybrook.edu/Skeena/373. That's where the homeworks and course handouts will be. We use Piazza as the discussion board. Everybody should register for Piazza. On the website is the Piazza, and the syllabus is the Piazza link. If you haven't already gotten on there, get on there. That's where I think most discussion should happen in there. I tell people about the partner system. Again, homework should be done in pairs, but it's important to understand how these problems work, okay? Because if you have a partner who's very good and you let your partner do everything, then you're going to find that it's going to work great up until the moment you have to take an exam. And that's when I am going to be encouraging you to, so I encourage you guys to make sure and work with it, understand it. We have a large number, an unusually large number of undergraduate TAs this semester, which I think is a very good thing. There's going to be at least one quote unquote recitation section, which means that there will be a scheduled time when these guys will be expecting, people who are interested to come into their Zoom room and they'll go through some problems that they've worked out in advance or something like that. But of course, the TAs are available for office hours. I'm available for office hours via Zoom at 11-ish on Tuesdays and Thursdays. You should be able to find that link in the Blackboard thing. Any questions? Okay. What else would we say? One thing that I will tell you is that when it comes to grading, I don't like, I happen to like teaching a lot. I happen to hate grading, and I happen to hate dealing with students complaining about grading. Generally speaking, I find that errors in grading are randomly distributed. Sometimes you get lucky, sometimes you get unlucky, sometimes we give you too many points and you don't tend to complain about that. What I find is complaints about grading are not uniformly distributed. And that's something to keep in mind. So I try not to have us give back points after they're graded, because I think it's unfair to the students who don't complain, okay? And I will be directing the TAs to not give back points unless there is something like an addition mistake, which is inevitable, okay, which is incontrovertible. Any questions? There's some questions about what the textbook for the course is going to be. The textbook is going to be the second edition here, okay? That's what we're going to be using as the textbook in here. Any questions for this semester? Okay, good. Any other questions here? As I keep going through the syllabus, there's probably some other ones. A bunch of points here that are in the syllabus. Well, some legal boilerplate that I want to make sure is that there is, if you are having, if you have some kind of a psychological, medical, learning disability type condition, you should consult the Student Disability Support Office. This is, I one semester had a student who, for after half the semester, after half the semester, the student announced to me that they were deaf. And in fact, that was, they were very good lip readers, but they should have been going through the Disabled Student Services Organization and things like that. If that affects you, you should go there. If there are, at the end of this, again, as I look at my syllabus, one thing that's also true is that this is a time when everybody is stressed out, and the world is a complicated place because of the pandemic and all of these kinds of things. I do encourage people to take mental health seriously at this time. Okay, I'm sure there will be stresses in the class. The class is not very important. The class is not important relative to your mental health. Okay, and there is a counseling center that I encourage people to go to if there are issues here. As far as cheating goes, if there are people who cheat, and the best way to cheat in here is to try to, typically on the exams or the midterms or the, the midterms or the final, I will take it up on the, through the, whatever the academic dishonesty policy is. And so I hope this does not happen. Okay, and this semester, because everything is online, some people may feel empowered that there are new ways that they can cheat. There are also new ways that we can check up and track you down. So I hope this is not going to become an issue. Any questions about that? Okay. One other thing that I have is I recognize with the homeworks, people do get busy during the semester. I allow each group one free 1 week extension on one homework. So there's 5 homeworks. 4 of them are done with your partner. And my hope is that people will, my hope is that people will, kind of take this seriously and anyway, kind of do this, not get caught up. But I do know that since people get busy, I give 1 free extension. Sometimes the dog dies, sometimes there's a problem in the family, sometimes you're just too overwhelmed with work. If you get to a point where this week, I don't want you to ask for an extension. I want you to turn it in a week later and write on your paper, this is my free extension. Okay? You don't have to ask me. You don't have to, I don't want you to ask me. Okay? But you get the extension for one of them. If you try to use it on a second one, we take off at 20% a day. So don't waste the free extension. Many people find they really like the free extension on the last homework because they don't get to turn it in then till the final exam, because that's the next time I get to see them. Any questions about the extension policy? Sorry about this. Any questions? One thing I will say is the 4th homework is actually very interesting. The 4th homework is one you don't do in pairs. That's one where there's a programming contest for coming up with the fastest algorithm for solving a particular problem. And that's to be done individually, and that's kind of an exciting thing. Okay, any questions about these rules of the game? Everything that I say in the syllabus is there. Any other questions about course policy?
I have a question about that course homework.
Okay, I'm having trouble hearing you.
for the fourth homework, can we use any programming language?
For the fourth homework, you can use any programming language you want. It's again, it's going to be on a problem, which I know is algorithmically hard. The difference in programming language isn't going to matter. Okay, the only thing that's going to matter is the difference in the algorithm. So you can use whatever algorithm you want. You can use whatever computer. If somebody says assembly language, assembly isn't going to be the answer. The answer is going to be the algorithm. And we'll talk, that'll become clearer as we get closer. Okay, any questions? Okay, I think I'm going to move on now. Let me see, how do I move on? Yeah, so this is the syllabus for the semester. We're going to start out, the introductory material is going to be on, I'm going to talk about what algorithms are. I'll talk about correctness. I'll talk about the big O notation and other mathematically oriented things here, like what logarithms are, because I think that's kind of important for algorithms. I'm going to then have a unit on data structures. All of you should have had CSE 214, the data structures course. And I will review, some of this is going to be review, but some of it is going to be understanding a deeper conceptual purpose as to why it is that data structures come in, where do they come into play, and we'll talk about dictionary data structures, we'll talk about hashing, we'll talk about priority queues, we'll talk about all the fundamental data structures that we build algorithms out of. Then we're going to have a unit on sorting. I know many people here have probably seen sorting 2 or 3 times in other classes, but analysis of sorting algorithms is a good way to get a sense as to how analysis works, what the basic design paradigms are in algorithms, things like that. And after that is going to be the first midterm. After the first midterm, we're going to start a big unit on graph algorithms, things like depth first search, breadth first search, directed graph algorithms like topological sorting, weighted graphs, algorithms for things like minimum spanning trees and shortest paths, things like that. Graph algorithms are a very fundamental topic. After that, we're going to talk about sort of brute force search, exponential time algorithms. We're talking about backtracking, combinatorial search, and that's what the programming homework 4 is about. That we're going to be dealing with a problem for which no fast algorithm is known, but there are good search algorithms and there are dumb search algorithms. And if you do search with the right kind of pruning, you can be amazingly successful. And if not, your program will run like a dog. And that's something that we will experience in, chapter 4, homework assignment 4. We have a contest for the fastest program. We have a prize for the fastest program. I may just give a prize for the slowest program, but that's not the one you want. Any questions? I will tell you, I got an email about, actually I can tell you in March from somebody who said, you don't know me, I took your class 20 years ago in algorithms. And I learned finally from you, I learned about what exponential growth is. And now that this COVID thing is going on, I cannot explain to my idiot in-laws about the fact that this is going to grow exponentially and that it's going to seem like nothing before all of a sudden it hits a wall and grows enormously. And so I thought it was interesting that that's kind of one of the lessons of the exponential search chapter is how, how the different asymptotic complexities really weigh in on things and what they mean. That I think is important. After that, we're going to go through a paradigm for algorithm design called dynamic programming, which is one of my favorite topics. Once you understand dynamic programming is incredibly easy. Unfortunately, until you understand it, it looks like it's magic. And so hopefully we will see enough examples that people will be able to start to start to understand where the magic is coming from. And hopefully they will understand it in time to go see before the midterm 2 is actually being given, because that's going to be one of the topics on midterm 2. Finally, after the second midterm, we're going to go through a unit on why there are sometimes not fast algorithms for problems. There's a unit on NP completeness. And, you know, this is a kind of an amazing thing that there are problems for which they don't have fast algorithms. But we can argue that they don't have fast algorithms, that there's no fast way to do, no way to do it efficiently. And for this is the concept of NP completeness. That's one of the really important ideas in computer science. And we will have, that will be the final unit we have before the exam. Any questions about the lecture schedule, the topics for the semester?
So on the syllabus that was included on your website, the PDF version, I noticed on November 10th, there's a Slack class. I'm not sure.
Oh, Slack
what that
class.
is.
Okay, so you guys maybe, you see that on this thing I have on my schedule, I said Slack class. You may get excited. Does that mean I'm going to be using that email service? And the answer is no. Slack means that I typically fall behind. And this is sort of me sagely saying I'm going to give myself a unit to fall behind before the exam. So it's just, this is the syllabus that I have on here is my dream of what I'm covering. And I allow myself a little slack in case I get behind. Okay. Any other questions about the syllabus? Okay. Let me just see if I can get my device to talk to me now. No. Okay, hold on a second. Let me get this here. Okay. Any other questions, logistical or anything like that? If not, I would like to start the material for the semester. And this is a course in algorithms. So a good question is, what is an algorithm? Let me just see if I'm capable of going forward here. This is not as smooth as I'd like. Okay, boom. No, so I'm having some trouble here. Okay, so what is an algorithm? An algorithm, I like to think of as the idea behind a computer program. All of you guys have written programs. All of you guys know what a program is. You know a program's supposed to do something. The algorithm is really the idea behind how it does it, okay? An algorithm, if it's interesting, is kind of a procedure, it's a recipe, it's a way of solving a general problem. And an algorithmic problem is something that we specify by describing the inputs that a problem has and describing what the desired property of the output is. An algorithm is then the thing that turns the input into the output. So let me just see if I can move on here for a second. And I am having still surprising trouble with this. Hold on. You guys see a new, okay, boom. Okay, so what is an example of a problem? The problem about the most famous algorithm problem you've probably seen is sorting. What is sorting? If I'm describing it as an algorithm problem, I specify what the input is, which in this case is a sequence of n numbers. We'll call them A1 ... to AN. And it specifies the desired output. Basically, the permuting of the input sequence, the rearrangement of them, so that the first one is less than all of them. The second one is is greater than the first one and less than all the other one, ... In fact, I guess I have it with less than or equal, okay, to kind of capture the idea that there can be ties in the input, okay? So an algorithm problem, we specify an input specification and an output specification. An algorithm is a procedure that will do, convert the input to the output. And a sorting algorithm and a sorting input is not the numbers 17, 36, 22. That's a specific thing we would call an instance. The input specification is a specification over all possible things that we can do. And for any given problem, we're going to be interested in finding algorithms that are efficient and correct. And when we mean by efficient, we mean in the sense of what the big O notation, which we will talk about next time. When we talk about correct, it means that it is always on every single possible input on any sequence of numbers. It produces a, an ordering such that the numbers are sorted from smallest to largest, okay? And the reason we're going to worry about this big O notation, again, I'm not going to talk about it today, but basically, it turns out that when you have large enough examples, the faster algorithm as per the big O notation will always beat a slower algorithm, even if the fast algorithm is running on a slow machine. For big enough, the great thing about algorithm design is that we can talk about these things in a relatively machine-independent way, okay? But in a way that does practically capture what's going on. Okay, let me see. And this still feels tight. Hold on. Boom. Okay, so what do I mean by correctness? Correctness of an algorithm is sort of the property that for every input, it returns exactly the specified output. And in sorting, again, if we want our sorting algorithm correct, it's got to work when the input's already sorted. It's got to work when they have repeated elements. It's got to work on every one of them. Now, for many algorithm problems, okay, particularly optimization problems, which say, find me the best thing, okay, it's often not correct that it's not clear that whether a particular procedure is correct, whether the algorithm always returns the right result, okay, the best possible result. In order to make sure that an algorithm is correct, this is why we have to prove correctness. For certain algorithm problems, okay, there are procedures that kind of sort of look like they're probably doing something. But unless we can prove that on every single instance, the algorithm produces the right answer, we call that an algorithm like that incorrect. Okay, it's wrong. And in this class, we're only going to be interested in correct algorithms that provably do what we want. Any questions about that? And one obvious thing about that is that if we're going to be dealing with, I have an algorithm that is provably correct, the problem had better be specified in a way that there is a correct answer. If I ask for you to give me an algorithm to find the best path to my office, is that a well-defined algorithm problem? I claim that different people would have different ideas of what best path means. Do you like going by the flowers at Javits? Okay, maybe you like the scenery better if you cut by Javits, or maybe you don't like a hill or something like this. If you want the shortest path, said I want the path to Skena's office from where I am that requires the fewest number of steps, that is a well-defined algorithm problem. And there's hope that we can find algorithms that will be able to find the one that requires the provably minimum number of steps. And in fact, we will do that later on in the semester. Any questions about correctness? Okay, good. Let me try one more time. I'm still trying to, okay, boom. So when we talk about algorithms here, we're going to need a way to specify what an algorithm is. And right now, I think these things will be a little bit clearer once we have some examples, which we'll be starting in a minute. we need some kind of a language to describe algorithms. And there are a couple of different ways that you can describe algorithms. One way is to describe it in English. The algorithm for sorting, let's say you want to describe what quicksort is. Well, you pick a pivot, you partition the elements so that all the elements less than the pivot are on the left, all the ones that are greater than the pivot are on the right, then recursively sort both sides. That's an English description of quicksort. Sometimes English is a good thing, but sometimes you need more precision. The next level of precision would be to write it in pseudocode, which is kind of something that is a language. It isn't a real language, but it kind of is close enough to a programming language that you think you could translate it into the programming language pretty easily. And finally, if there's a really tricky algorithm or one that you really need to run in order to see what's going on, you might want to describe it in a, with a real programming language. What I find is when I'm describing algorithms, the way I like to do it is I describe the idea of the algorithm in English. What's it trying to do? If there are details that require some precision to get right, I will use a pseudocode for that, okay? And I will, as often as possible, try to make a picture to kind of show what's going on, okay? So that when it comes time normally, what people submit on the exams, when I say, give me an algorithm, sometimes people write random pseudocode without any, it just looks like garbage, okay? Can't understand it. If there's an idea that's made clear, what we're trying to do, that can be written in a line of English. Then maybe we can interpret the pseudocode better. If there's a picture of what your algorithm is doing, then it's easier to kind of understand what's going on in your head, okay? And so the algorithm stuff, expressing it, is about what's going on in your head. Okay, any questions about any of this? Okay, this is kind of all the mechanics of what an algorithm is. Any questions about that?
When we do your homework, are you expecting English, pseudocode, or it doesn't matter?
Okay, so how do I specify? What I expect is to be able to understand what your solution is. So this is not, to be honest. And that requires writing things at the proper level. Certain problems, getting the detail right is the tricky thing, okay? And something like that, I'd want the detail level of pseudocode. Sometimes there's a big picture idea that's really, once you get the idea, the details sort of are obvious to anyone that understands the idea. So I would be writing it, typically I would be writing something at an idea level, okay? And if you get the idea, then I can believe what's going on. And if there are details, the pseudocode can be used to clarify that. This will become maybe a little more obvious once I give you the examples, starting in the next section. Any other questions about this? Okay. Let me keep going. Okay, I would like to now start by giving us a first honest algorithm problem, which is a problem that I once encountered in, I encountered in a company, actually. A company called me in as a consultant on this. And it was a company that did printed circuit testing, printed circuit board testing. Those of you I know, probably most of you have a cell phone. For the purposes of this discussion, you took that cell phone and you slammed it against a wall. After the case broke, you would find on the inside the electronics. The electronics would include a printed circuit board with various chips kind of soldered to that board. And the purpose of the this company that I was going to is that they made a robot whose job it was to solder, okay, the chips to boards, printed circuit boards. So if you think about it, on the back of your iPhone, there is going to be, in the iPhone, there's going to be a circuit board. Actually, do I have the ability to draw? I am angry I don't have the ability to draw here. I'm not sure I know why, but I'm going to have to double check that. Actually, do I have the ability to draw on here? This is an interesting thing. Do you see this drawing?
Yes.
People see this? Okay. So let's, okay, this is probably a bad thing. If you look, shatter your iPhone and look at the back of the printed circuit board, you're going to see something that looks like this. These are where the wires on the back of the chip, okay, have to be connected to the board, okay? And the job of a, the assembly robot is that for every one of these spots on the circuit board, it needs to be hit by a solder iron, a big an electronic thing that is hot that will melt metal to it. And manufacturing an iPhone requires basically programming a robot to do this assembly. And you could imagine the robot going bzzzt to solder that point, bzzzt to solder this point. Does everybody see my pen when I'm doing this? Or is that not visible to you?
Yeah, we see the.
It's visible.
So do you see the pen?
Yes.
Yes, we see it.
Okay. So you see me go bzzzt, 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 bzzzt. It'll take a long time to assemble the circuit board because the robot's got to move its arm all the way across the board. Much better would be if we could program the order of the points so as to minimize the amount of motion the robot has to do. Does everybody kind of see that? If you do it that way, then in fact it will take less time to manufacture, less time for the robot to connect the things. My claim is that the robot company, and in fact that's what they wanted to know, wanted to be able to take a circuit board and take the circuit board and basically have me give it an ordering of the points on the back of the circuit board, so that the robot, if it's soldered in this order, would require the smallest amount of movement in order to do the job of connecting it. Okay. So actually, let's see. Okay, now with the annotation, this is a problem. I guess you now see my blue thing, don't you? Is there any way to erase the thing? Eraser. Hold on. Boom, 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 boom. Okay. So what is the problem that this robot thing had to do? The input is on the left, the points on the back of the circuit board. The output is the order of the, the output is the order of the points to visit so as to minimize the total travel time. Does everybody understand this problem, or does any questions about that? So can anyone give me an algorithm to take as input the XY coordinates of every one of these points and output the order for the robot to travel to minimize the work done? Does anybody have a proposal on how to do it?
I do.
How do you do it?
If you have like an initial point to start from, you can go to the nearest neighbor and continue to do that until you don't have any points left to annex.
So does everybody see what he's saying? He's suggesting what we would call a nearest neighbor idea. Start from one point, find the closest neighbor, and then go there. And then from this point, find the closest neighbor to it and go there. And find the closest unused neighbor. You don't want to repeat, okay? But after every from every point, we're going to make n iterations and find the closest point, okay, in each case. So let me see if I can do this, okay? This is what we call the nearest neighbor tour. Start from one point and walk to the nearest neighbor, and then keep doing this, nearest unvisited neighbor, and keep going. Now, we were talking about pseudocode versus, English. This red thing is the English description. Start from some point, walk to the nearest neighbor, keep repeating until you visit all the neighbors. That's English. The black thing here is pseudocode. It's a programming language that specifies what I'm doing, okay? But it doesn't, doesn't give syntax errors. It's whatever I want it to do. Pick a first point. Let P be the latest point. While there's still unvisited points, increment the counter of the number of pointers I visited. Let PI be the closest unvisited point. Visit it, and then repeat. Okay? Any questions about the nearest neighbor tour? Does everybody agree that given any set of points, it will find an ordering that visits all the points?
I have a question.
Yes.
So isn't it going to be wrong? So at some point you are going to, let's say you choose all the nearest neighbor, but you went on the other side of the circuit board, let's say, and then the nearest neighbor is actually located where you began. I mean,
okay.
If you have two nearest neighbor like in the opposite direction, what are you going to do?
Okay, so you're saying that sometimes there might be two nearest neighbors. Which one should I go to? Does it matter? The real question that you're asking is this thing an algorithm or is this thing wrong? Okay, and if you go to, if we take a look here, if I can get my act together, and again, this is surprisingly challenging. Give me 1 second here. I don't quite know why this is so challenging because I've been doing it with the other class surprisingly easily. Do me a favor, hold on. Okay, hold on. Okay, what about this case? Suppose the points were on a line where, let's center it around this point at x equals 0. Let's say there were 2 points at points -1 and 1, another point at -5, another point at 3, another point at 11, x equals 11, and x equals -21. What is interesting about these points? Suppose I start at point 0, x equals 0. Notice that as the caller suggested, I could either go, my nearest neighbor is a distance 1 away from me. I could either go to the left or the right, okay? Suppose I go to the left. Now, what is the nearest neighbor, nearest unvisited neighbor to the point x equals 1? What are the nearest neighbors to that?
-1.
-1 is a distance of 2 from it. And what? What else is a
3.
distance? And 3 is also a distance of 2 of it. Do you see how this example, there's 2 different ways that I could go? What if I pick going to -1? Now, what is the nearest unvisited point next to -1?
-3. -3 and 3.
It could be -3 and no minus. Actually, I think that's -5 and 3. Am I right? And what is the distance to these points? Both of them have a distance of 4 from where I am. I might as well pick it arbitrarily. I'm going to go to the left, go to the right. Does everybody see that if I keep guessing wrong on breaking these ties, I'm going to go left, right, left, right, left, right on my tour. Where if I guessed right, what would I do? I'd start from 0. I'd go all the way to the right, jump back all the way to the left, and then come back home. Does everybody see that the solution on the bottom is substantially shorter than the solution on top? The solution on top is the what was given by that nearest neighbor heuristic. So what does this example prove? This example proves that the nearest neighbor heuristic is wrong. It is an algorithm that is incorrect. It does not guarantee the shortest possible tour. Any questions about that? Do people see this? This I find an illuminating example. One thing that you have just learned that some of you may not realize is sometimes programs are not wrong. The algorithm is wrong. If you implement this program algorithm, that nearest neighbor thing perfectly, it will not find the optimal solution, okay? Because the algorithm is wrong. Any questions about that? Any other ideas on how we can find the shortest tour for this robot that visits all the points?
A closest pair approach.
What was that?
A closest pair approach.
Okay, so someone who I think has read ahead, okay, which is not necessarily a terrible thing. Hold on a second. Boom. Another idea might be instead of, if we think about where we went wrong with that, we started at point 0, and once we made that decision, whenever we always go to a neighbor, kind of decisions are fixed, maybe that's the problem. Another idea might be, instead of starting someplace and walking, another possibility might be to keep using short edges all over the place, unless they cause a contradiction. So maybe what we should do is start out, we've got those endpoints on the plane, find which pair is closest and connect them. Then look again, which pair of points is then closest? Maybe it's another pair of points out over here, okay? And we would get into trouble if we connect a pair of points that will cause something to close off. And again, I'm sitting here unhappy. I cannot write on my new expensive iPad, but let's see if I did annotate. We agree that if this, and this were my points, okay, it would be bad if this was my closest thing, this was my closest thing, and then I took this, because now I've got a tour that's closed and I still have another point to visit. So that's not something that's allowed. And it would be bad if I started building my tour where I took this edge, uh-oh, now we're in big trouble. Big trouble. Let's go back to this thing. Let me see if I can go back here again. Are we zooming through here? Hold on. Maybe I'm going to have realistic. Okay, can I draw now is a good question. Still don't seem to have the power to draw. We would have trouble if, sorry about this. We would have trouble if we ended up making a three-way join. Because in a tour, every pair is going to have a neighbor going in and one going out. So what's an example where this closest pair idea can do badly? Okay, if we take a look at this, okay, here we've got a set of points, 6 points on a forming, I guess, some kind of rectangle. Suppose it's the case that the points, the 2 rows of 3 points, suppose the points are, the rows are slightly closer than the points are apart according to the x coordinate. This would be 1 minus epsilon. This length would be 1 plus epsilon. If we did the closest pair heuristic, what would we do? We'd say the green edge, that's something of 1 minus epsilon. The orange edge, that's 1 minus epsilon. The purple edge, that's 1 minus epsilon. Now there is no really short edges left, okay? Maybe I'll now take this one, which is of edge 1 plus epsilon, and this edge, which is of edge 1 plus epsilon. If I do that, I've got that little snake now, but the only way to close off my door is with this big, long diagonal edge, that kind of reddish edge. It should be clear that if instead I only walked around the outside of it, like on the right, I would have a tour of size 4 times 1 minus epsilon, 1 plus epsilon, plus 2 times 1 minus epsilon, okay? It should be clear the tour on the right is shorter than the tour on the left, okay? It's something like about 22% shorter, okay? So if you believe that, the heuristic where we're constantly trying to take the shortest edge that won't cause a contradiction isn't right. Both of these algorithms are wrong. They do not always give us the correct algorithm answer. Any questions about that?
I had a question about your implementation for the closest pair.
Yeah.
In that implementation, if you end up picking, like as it says here, if you end up picking the shortest possible, like closest pair initially, as in your first iteration, then after that, so the threshold D would be set so low, so wouldn't any other greater closest pair length not be qualified to be selected because that's greater than D?
Well, no, what I think is, what this thing is doing, oh, okay. You say you don't like my pseudocode. You think I've got a bug. And I think what I think you want me to do is this D equals 0 infinity. This probably should be inside the for loop. Does that make you feel better?
Yes. Because that
Okay.
way, I think every time you iterate, it would just have to be less than infinity to be a closest pair, right?
Okay, so this is actually very instructive. Does everybody see what he's kind of saying here? That what this is saying is, here I said, always find me the closest unused pair. That's English. If you have to program it, you've got to put it as a loop, right? And how did I keep track of find what the shortest pair was? Well, I had a variable D that would count the length of, keep track of the length of the shortest edge I haven't used yet, right? So for each pair of endpoints of partial paths, if the edge between two of those endpoints is less than the shortest one I know, then basically keep track of that and update the shortest one I know and connect those two, ultimately the closest pair ultimately by an edge, right? Now, what he noticed is that for this to be a correct thing, this resetting of D to infinity has to be done inside the loop, between the two for statements, okay? So what's instructive about that? It shows that pseudocode, because I'm not running it, and because, you know, it can look very nicely typeset, but it's not necessarily correct, okay? It might be clearer to actually describe it in English, okay? I think that in this case, the description in English was clearer, okay? But anyway, this was a bug, and if somebody sends me email, I may fix it in the slides for future years. Any questions about that? Okay, any other questions about any other ideas for an algorithm for solving this problem?
Can I do, yeah, I was just gonna say this.
So one other possibility is I try all possible tours. Any tour is a permutation of the points. Those of you who took AMS 301, how many permutations are there on n things? I have n points. How many different orderings are there of n points? I'm
N
seeing
factorial.
people answer n factorial, okay? And n factorial is the right answer. N factorial is a big number though, right? So what we could do is construct for every one of the n factorial permutations, we could, compute what the cost of the tour is on that permutation. If the cost of that tour is smaller than any tour that we've seen so far, that's the current champion. And after we go through this for loop n factorial times, we will visit every single tour and we will know that it's right. Okay? Any questions about it? Does everybody see that if we try all possible orderings, that will give us a correct algorithm for this problem? Is there a problem with that? Okay, are we now happy that we have an n factorial algorithm? Are people happy or unhappy?
No,
No, why are you not happy?
it's not computationally efficient.
So n factorial can be a bad thing. 20 factorial is bigger than you could possibly hope to wait for, okay? And 100 factorial is bigger than the number of atoms in the universe. So you could only hope to solve a very, very small circuit board to optimality by doing exhaustive search. So what's interesting about this problem, I called it the robot tour problem, but this is actually a famous problem in algorithms called the traveling salesman problem, where you imagine a traveling salesman person, okay, who wants to visit a bunch of customers. They want to find what is the ordering to visit the customers so that they use the smallest amount of gas, okay, or traveling time. Bottom line is, we will show later on that this traveling salesman problem is one of these NP-complete problems. And there is no fast algorithm for it, okay? That is both efficient and correct, okay? But we will see many times that we are going to get lucky and there are both efficient and correct algorithms. Any questions about that? Okay, what I'd like to do now, to be honest, is skip over the next one, maybe at least for now.
I have a question
Yes.
about the previous problem. So previous problem, the last solution would be inefficient, but that would be a correct solution.
That would be correct. Why do we know that if we try all possible tours and take the cheapest tour? Why do we know that that's the cheapest possible tour? Well, we considered all of the possible tours. There's only a finite number of them. There's only n factorial of them. If we construct each permutation and score it and keep the smallest one, we will find the cheapest ordering. Okay? So that's why we know that it's got to be correct. The fact that it takes n factorial time, because we've got to do at least one operation for each tour, and probably more, that's a sign that it's going to be very inefficient. Okay? Now, it may be, as in this problem, there might be no algorithm that is both fast and efficient, both efficient and correct. Okay? But one of the cool things about it is by the end of the semester, we will be able to tell if, for many problems, that if we can't find a fast algorithm, it's not just that we're being stupid, it's that there isn't a fast algorithm. And that's one of the things that could be exciting at the end of the semester. Any other questions about that? Okay, good. So,
Sorry.
yes.
Is it possible that there could be, and we just have not found it yet at all?
Okay, so the question is, has to do with something about NP completeness. There's a certain amount of technical weasel words that we will have to discuss at the end of the semester. But in my mind, if you're asking me, okay, once we prove that it's NP complete, it means there's no fast algorithm. I sleep very well with that assumption.
Okay.
And we will talk about the details of what that means precisely at the end of the semester. But
Okay.
but it's a very powerful, there's a little bit of weasel room there. But on the other hand, it is a very powerful idea that we can argue quite convincingly that there's no fast algorithm for a problem.
Okay, thanks.
Okay, very good. Okay, what I would like to emphasize now, that I hope people are starting to get, is this vision that an algorithm has to be either proven correct, or a fake imposter algorithm has to be defeated by showing counterexamples to it. So one of the important algorithms that, let's say skills that an algorithm designer has, is the ability to show that an idea doesn't work. Searching for counterexamples. A counterexample is a instance that will break the algorithm. We saw that, for example, on the nearest neighbor, okay, idea for heuristic for traveling salesmen. We saw that if we could trick it by having two nearest neighbors, we could show that if it picked the wrong one, something bad would happen. Okay? So an important problem, which is one of the things we'll test in the next daily problem, okay, is this act of looking for examples that will break a heuristic. A heuristic is a fancy term for an algorithm that isn't correct. That's, I guess, in my mind. Okay, it's a procedure, it's an idea, it's a rule of thumb, but it's not always correct. How do you find bad examples, counterexamples that break heuristics? Well, one thing that you could do is try all possible examples for small sizes. If we think about the traveling salesman problem, how many different ways could you arrange 4 points on the plane? Okay, there's probably not that many of them. Maybe if you try all arrangements of 4 points, you'll see some kind of a problem. Another good idea is to look for places where there are ties. When there is a tie, that's a very, very good, useful thing to break a heuristic, because now, unless your heuristic tells what to do on a tie, it's going to pick the point arbitrarily. You can say, well, if it doesn't know which one to pick, maybe it'll pick this one, and that one would be the wrong one. Another idea for trying to demonstrate incorrectness is to think about extreme things. You've got big distances, let's say points that are very far away, and you've got little distances that are all kind of tiny points that are in a cloud, or maybe that are even on top of each other. Now we've got examples where there are points that are, very short and very, very far. Maybe we can reason about these kind of examples more easily, okay? So being a good algorithm designer is being clever about knowing when your idea is wrong, and the way to tell that your idea is wrong is to show me an example that rigorously proves that it's wrong. Any questions about that? No, okay. The final thing that I'd like to talk about today is something that you guys kind of know, but just to sort of remind you that you know it. You guys presumably have taken classes where you prove things. So again, ideally we want to prove that algorithms are correct. How can we prove that algorithms are correct? Well, you've got to know something about mathematical proofs. Counterexamples are great ways to prove that an algorithm is wrong. But occasionally you'll stumble onto an algorithm that is correct. If so, how do you prove that it's right? Well, one of the ways that you learn to prove things that is going to be very, very useful as a technique for proving algorithms correct is induction. Does everyone remember mathematical induction? This was something where I assume that this was beaten into your head in CSE 215. Okay? Mathematical induction is something where you kind of want to prove something for all n, maybe all instances of all sizes. How are you going to prove it? Well, we're going to start by showing that it's obviously true for very, very small things. Like, for example, for 3 points, do we think that a particular heuristic is going to be right for 3 points of traveling salesman? There's only one way to connect 3 points into a tour. Is that going to be the optimal way to do it? I think the answer is yes, because there's only one possible tour on 3 points. Then you're going to assume that it's true for all n up to a certain point, up to n minus 1. And then you're going to reason that it's true for all n, based on it being true up to n minus 1. So what do we know? Again, if I had my pen, I think you guys are going to get spared a proof because I am not in a mode where I am writing this naturally. But how do you prove, for example, that the sum of the numbers up to 1 to n is equal to, is equal to n plus 1 over n, this thing? Well, what do we know in general? The sum up to n plus 1 is going to be n plus the sum up to n minus 1. That is going to be, by this formula, if the inductive assumption is true, that's going to be n minus 1 times n over 2. And my claim is that this is going to sum up to be that. Okay? I think if you've seen an inductive proof, you know what I'm talking about. But basically, induction is a good way to prove things correct. And especially for recursive algorithms. And I guess the one idea I'd like to leave you with is that recursion and induction are really kind of the same thing. Recursion also deals with a basis case. Recursion also deals with a general, a general way to take a large thing and break it into small things. And the correctness of the recursive algorithm kind of assumes that all the answers to the small things are going to be right. If you see this, you'll understand that induction is a good way to prove things and that it's very closely linked to recursion. That said, we will talk about it some other time about proofs. For now, we're thinking about counterexamples. And for next class, turn in the daily problem before class starts, and I look forward to going through with you guys then. Any questions? If not, I leave you in peace till next class. Thanks for your attention.